In this problem, we are to solve the following equation for x. Because the input variable x is in the exponent position, we call this entire equation an exponential equation. To solve exponential equations in this class, we will follow a four-step process. Step 1 in that four-step process is to isolate the exponential term. The exponential term would be the part of the equation that has the input variable along with its base. So this means we need to isolate this, meaning we need to get rid of the 20 that's being multiplied to the other side, and the 7 that's being subtracted needs to be moved to the other side. So step 1 will actually take me a couple lines. So step 1 is actually two steps. The first thing I'm going to do is add 7 to both sides, in which case this simplifies down to be 0 on the left-hand side, and on the right-hand side I simply get 17. Next, since the 20 is being multiplied, I will divide both sides by 20, and since 20 divided by 20 is 1, we usually don't write multiplication by 1, I would just be left with e to the 3x plus 5 is equal to 17/20. I'm done with step 1. So step 2 simply says take the natural log of both sides. For this to work properly, you have to do step 1 before you do step 2. But taking the natural log of both sides is as simple as just writing the ln and plugging the left-hand side into that function. And then taking the ln of the right-hand side as well by writing ln and plugging the right-hand side of the equation in the parentheses. So doing that, just copying this down and copying the 17/20, I'm now done with step 2. The reason to do step 2 is that whenever you plug in an exponential expression into a logarithm, things can be usually simplified down, in this case such that we will no longer have an exponential equation. In fact, step 3 says if the base is e, and by the way, if the base isn't e, you'll have to refer to a different video of mine. But since the base is e, we are going to simply use the property that says that whenever you plug in a base e exponential into a base e logarithm, things simplify so that the ln and the e basically cancel each other out, leaving you with whatever the exponent is. In my case, I have the ln of e, and my stuff in the exponent would be 3x plus 5. So according to this property, the ln and the e somehow simplify out, and I'm left with 3x plus 5. So when I replace all of this with 3x plus 5, I will no longer have an exponential equation, I will have a linear equation. So that would be 3x plus 5 equals some number, which I don't know unless I touch my calculator. I have no idea what the natural log of 17/20 is, but it's some decimal. I am done with step 3. Since I'm not done solving for x, I still have to solve the equation for the input variable. But because it's linear, I don't give any directions how to do that, because to solve this linear equation is the same kind of steps you did up here. If something's being subtracted, add it. If something's being multiplied, divide it. In this case, I have something being added, so I'd have to subtract 5 on both sides. And if I was to write that all down in one line, it would look like 3x equals, because plus 5 and minus 5 is 0, and we don't usually write adding 0. And then on the right-hand side, since I can't combine these two, because I don't have a decimal approximation of this yet, I'll just copy it down and then write subtract 5. Notice the parentheses do help us remember that the natural log of this number has to be done first and then the subtraction of 5. It would be incorrect to combine this fraction with the subtract 5 first and then take the natural log. I have one step left to solve for x. Since the 3 is being multiplied, I'd have to divide both sides of the equation by 3. When you do it to the right hand side, make sure the division bar goes all the way across. 3 divided by 3 is 1, and 1 times x is simply just x. So as an exact answer, I'm going to leave my answer like this, and the power of that is, if ever you needed 1,000,000 decimal places, you could type this into a computer, tell it to give you 1,000,000 decimal places. You might have a small weight on your hands, but it would give them to you. As soon as we type this into a calculator and get a rounded version, whatever we round it to would be the most accuracy we'd ever have. I'm going to actually do that on a calculator right now. I turn my calculator on. I'm going to type in the natural log of 17/20, subtract 5. Now I have a choice. I either have to put parentheses around everything I just wrote and then hit divide by 3, or to make sure the subtraction gets done before the division, I can simply press enter and then type divide by 3. So to get a 4 decimal place approximation, I would say that's negative 1.7208. Because this digit here is less than 5, I'm going to leave the 8 as an 8. Also notice that now that this is not an exact answer, I'm not going to write equals. I'm going to use the approximate symbol. I like to call it squiggly equals to let people know that this is a rounded version. It actually is possible for you to do a problem where the answer as an exact form only has 4 decimal places, And if your answer only had 4 decimal places and you gave all 4 decimal places, it would be an exact answer. For this problem, however, I have something that has infinitely many decimal places. As soon as I typed it on my calculator, I already got a rounded version of that answer because the calculator took it upon itself to round that number to 9 decimal places from the beginning. So what you're seeing here is not an exact answer on the calculator. You're seeing this out to about 9 decimal places.